Hello, welcome back to our side stage. I would like to introduce you Maciej Kalka, researcher at vlayer, and where is zk in zkTLS.
Thank you, Artur. So in the next 15 minutes, I'd like us all to find the zk in zkTLS. There's a lot of hype around recently, a lot of maybe small controversies with the naming. So let's find out where's the zk at. So to start with zkTLS, we need to remind ourselves of TLS again. So TLS is basically the most important protocol in our daily web surfing activities. It's a protocol between client and server, which securely encrypts all the data traffic between us on web browser and the server. So it's hard to imagine the internet, the Web 2 without TLS, but in the verifiable era of the internet, it's not enough because the transcript from the TLS session is hardly verifiable. Client has the keys to encrypt the transcript, so he can easily forge any transcript. It's always good to think of a screenshot reference. You can easily Photoshop it. You can do exactly the same with TLS transcript. So that's why we need extra solution to bring the verifiability to TLS protocol, and that comes with so-called multi-party computation TLS, MPC TLS protocols. So we have new colors over there. Most importantly, there comes a third party to the game. We call him notary because he is responsible to sign the transcript in the TLS session. So the whole signature thing happens in multi-party encryption decryption phase, then notarization. Session is terminated. We check equality. We check the security of the protocol, and we can deliver the data to be verified at external verifier with this signed transcript, so it's easy to verify. So that gives us MPC TLS. One of the examples of such protocol is the great TLS notary protocol. So to sum it up, we have, with MPC TLS, we have all the guarantees of original TLS protocol, but additionally, we got the data portability and data verifiability, which are not easy to achieve with TLS. But importantly, the MPC TLS, so TLS notary, do not result in a proof. It do not result in zk, but just signed attestation. The notary signs the transcript, and that's what we get. Verifier can verify it, but it's not a proof. It's not a zk thing. So then, why everyone calls it zkTLS? I don't want to go into controversies if the naming is good or bad, but certainly the zk is involved in there at least once, but maybe twice. So to start with, we find zk in data verification step. That's where our solution at vlayers comes in handy, because with the signed transcript delivered, we can wrap it in non-interactive zk proof. We can wrap it in snark, prove some statements about data, make it more portable, and finally make it verifiable on chain. So that's what we can do. For example, if the transcript states that our residence is in Poland, with non-interactive zk proof at data verification step, we can just prove that it's outside US and provide that information to external verifier. OK, that's cool. That's a cool feature, but it's still outside the main protocol. So there's still a question if we should name the multi-party computation TLS, MPC TLS, zkTLS. And it happens that right there in MPC phase, there's another instance of zk. Right in the heart of the protocol, we use interactive zk, whole different zk protocol, to prove equality check of the notarized transcript. So to see how is it done, we need to dive deeper into this MPC phase of TLS notary. So the protocol that is responsible for either encrypting the data within two parties, client and notary, or decrypting the data together with client and notary is called DEEP. It's double execution with asymmetric privacy. And the name says it all. We have two parties who mutually execute the protocol in order to learn the output together, but to plugging in only their private inputs. So the client always plugs his key share from TLS session and plain text. Notary always plugs his key share. And the point of the whole protocol is that notary never sees the plain text. So he will sign the plain text later, but he will never see it. So if we take a more general look on how does DEEP look like in structure, in this kind of black box fashion, we can distinguish 3 phases and 2 black boxes. So the first one will be leaky MPC, leaky multi-party computation. And that will be the phase where client and the notary will deliver the private inputs and receive the same output. So they will deliver the key shares and will receive ciphertext, for example. And these 2 steps are realized with garbled circuits, oblivious transfer, within 2 phases, setup and evaluation. So those are typical phases of any GC protocol, any MPC protocol. We need to set up our garbled circuits and then execute them. And what's noteworthy is that this protocol is called leaky. So it's not necessarily maliciously secure. To make MPC maliciously secure, we need either way complicated solutions, cryptographical solutions, which are computationally expensive, or we can do the trick with equality check using interactive zk protocol. So that step, it do not involve any, it do not commit to receiving the output function, but it ensures that the output function was calculated in secure manner. So to see how this is achieved, we need to take another deeper look into that part. And this is, again, achieved using garbled circuits based on, in TLS notary, it is based on this great paper, JKO 13. So the TLS session is over. Notary no longer needs his key share. So he can reveal his key share to client. He loses privacy, hence we have asymmetric privacy, but he does this to assure security. He does this to assure that the plain text was encrypted correctly. So they run the encryption scheme within garbled circuits. The clients run this to ensure that the notary behaved honestly. Why is it zero knowledge? Because the notary never learns either plain text or the client's key share. So he gains zero knowledge about client's private inputs, but he learns if everything was proven honestly. So he learns if the plain text encrypts to the notary's ciphertext. And why is it interactive? Because notary gives away his key share. They need to interact within each other. So it's whole different zero knowledge story than snarks or starks, but it's necessary to keep the protocol secure. So to sum it up, the first point for you to take home is that you can look at the MPC TLS protocols as such black box. You do leaky MPC to compute the output, and then you plug in IZK, interactive ZK protocol, to make it secure. And this gives the pathway for optimizations. Or you can either optimize for MPC, you can find more optimal garbled circuits, you can find more optimal oblivious transfers. So that's one way to optimize the stuff. There are a lot of papers in there. And you don't need to optimize for maliciously secure MPC. It's enough for it to be leaky. And the second way of optimizing is to find another interactive ZK protocol. So there are a great progress in there. For example, the Quicksilver paper, which is super fast. So yeah, that's one insight. And the second insight is the answer to the initial question. So I want you to remember that ZK in zkTLS happens not only on verifier's side, where it can be non-interactive, our ordinary ZK snark, which will be app-specific and will make the whole pipeline great for verification on chain, for example. But also the ZK is right there in TLS notary, in MPC TLS protocol hard. But there it is an interactive ZK, which is based on garbled circuits, oblivious linear evaluation, but it's always there. So you can't have MPC TLS, you can't have TLS notary, maybe more specifically, without interactive ZK inside. So I wanted to thank TLS notary team, who provided us with great insights so we can write our report on web proofs, available soon, and also more technical report on TLS notary protocol, hopefully in September, will be available for you. Thank you all for listening.
Do we have some questions? No questions? Okay, so last but not least, I would like to invite Adam from Hinkal.
Thank you.